Good day, grade 12 learners. Welcome to today's physical science lesson. My name is Mashudu Mamburu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saipono Discovery Center. Today we'll be dealing with still knowledge area, chemical change. Remember, we're talking about plus minus 92 marks in your final exam. That's a lot of marks from there. We'll be dealing with the topic referred to as galvanic cell is under electrochemistry. Remember, electrochemistry has galvanic cells and electrolytic cells. So for today, we're focusing on galvanic cell, which in the question paper for final and prelim is usually in question 8. So we'll be dealing with that, and I will be ensuring that you have understanding of this topic and you have confidence when you go to do the questions. So I hope you are ready. I hope you are having your calculator next to you. I hope you are having your table 4A and table 4B. Very much important that you use this table that you find at the back of your question paper. They are written table 4A, table 4B, which is the standard reduction potential tables. So when you are dealing with question 8 and 9, definitely you need these tables because they are going to guide you. I have mine next to me here. Time to time I'll be referring to it. I'll be telling you to refer to it as you answer questions. So it's important that you have table 4A, table 4B when you are dealing with this question on galvanic cells. So without any wasting of time, we'll move now to the lesson itself. We'll start with the lesson objectives to say what are the objectives of this lesson. The first thing that you must know, in physical sciences, we are always saying definition according to the exam guideline. So the first definition, which is the most important definition in this topic, is defining galvanic cell. Remember, galvanic cell is a cell. Galvanic cell is a cell. So you got to define galvanic cell as a cell in which chemical energy is converted to electrical energy. I know you have been busy with electrodynamics where you were talking about your motors and your generators. And then there you were talking about mechanical energy. When you're talking about generators, you said mechanical energy to electrical energy. But when it comes to paper 2, we don't talk about mechanical energy, we talk about chemical energy. So it's important that you understand that galvanic cell converts chemical energy to electrical energy. And then other definitions which you must know is to define oxidation, which I know you have done this in grade 11. You were able to define oxidation and reduction. You can do that in terms of electron transfer. So always when you're answering the question, you will check whether the question wants you to define oxidation or reduction according to in terms of electron transfer or in terms of oxidation number. So you can define oxidation, reduction in terms of electron transfer, or you can define oxidation reduction in terms of oxidation number. So don't be too excited when you're answering the question. Always check whether the question requires you to refer to electron transfer or to oxidation numbers. Now, when you define oxidation and reduction in terms of electron transfer, you will say oxidation is loss of electron. Oxidation is loss of electrons. Hence, we are saying oil there. Oil there. Oxidation is loss of electron. And reduction is gain of electrons. That's why we're saying rig. So we are rigging the oil. Oil rig. We're saying the reduction is gaining of electrons. So always this will help you to be able to remember what is oxidation, what is reduction. And then in terms of oxidation numbers, when you define oxidation in terms of oxidation numbers, you will say oxidation is an increase in oxidation numbers. I know you know oxidation numbers that you have done in grade 11 as well. And then, for example, if you are having, say, zinc forming zinc 2 plus, because it has lost 2 electrons, you will see that the zinc oxidation number was 0, and then the oxidation number becomes 2. So the increase in oxidation number, we refer to it as oxidation. So you can define oxidation as increase in oxidation number. I've used an example of zinc there. Reduction, you can define it as a decrease in oxidation number. In this case, you can have a copper 2 plus gaining 2 electrons, to form copper. And then you can see that copper 2 plus in the reactants, it was 2, and then in the product side is 0. So you are able to see there that reduction is the decrease in oxidation number. You see copper 2 plus has decreased to copper. So it's important that you have that. Now the next definition that you must know is the definition of an oxidizing agent. So we're saying an oxidizing agent is a substance that is reduced. So the oxidizing agent is not oxidized. The oxidizing agent is reduced. Itself is reduced, but it's an agent that will help the other one to be oxidized. So you're able to see that. So we're saying oxidizing agent will gain electrons. So in this case, copper 2 plus is the oxidizing agent because itself is reduced to copper. Copper 2 plus is reduced to copper, but the oxidizing agent is not copper. The oxidizing agent is on the reactants, is copper 2 plus, the one that gains electrons. That is our oxidizing agent. The reducing agent, we're saying, is a substance that is oxidized or that loses electrons. In this case, zinc loses electron, or zinc is oxidized to zinc 2 plus. Hence, we're saying zinc is our reducing agent. So you can see that the reducing agent and the oxidizing agent are on the reactant side. On the reactant side, we have the reducing agent and the oxidizing agent. So I hope you always remember that, to say the oxidizing agent is a substance that is reduced. The reducing agent is the substance that is oxidized or that loses electrons. And you must be able as well, according to our exam guideline, define the anode and the cathode. Remember, the anode, we're defining it as the electrode. I know you have been doing organic molecules where you did the suffix and the prefix. So it's important that you always take what you have learned before and bring it here to say, okay, we know that the suffix here, when you say anode, the suffix will be ode there, which is from the word electrode. So you are able to see that, okay, the anode is an electrode. So the anode is the electrode where oxidation takes place. It's just a matter of English. You can say is the electrode where oxidation occurs. You are still saying the same thing. The electrode where oxidation takes place, that is what we refer to as the anode. The anode is the electrode where oxidation takes place. So I'm happy. It's not saying the anode undergoes oxidation. It's saying where the anode is, the reaction that will take place is called oxidation. Hence we have a short there, we can say an ox, so that you always remember that it is at the anode where oxidation takes place. So we're saying at the anode, oxidation will take place. And then we are saying now the cathode itself, it is the electrode where reduction takes place. I want to as well emphasize here that it is the definition is not saying the cathode undergoes reduction. It's saying where the cathode is, the reaction that will take place is reduction. Hence we say red cat here. Red cat, for you to remember that where the cathode is, that's where reduction takes place. So you are able to see that we have the cathode and the anode, and we're going to unpack all this as we move with the lesson. So for now, I'm reminding you all this, and these are the definitions that you are expected to know. They are simple. Know all of them with confidence and be able to answer questions. As we continue, we have now what is referred to as the electrolyte. Electrolyte, we're saying, is a substance of which aqueous solutions contains ions. I'm happy. I'm talking to learners who have done acids and bases. They've done hydrolysis. They know that when a reaction of salt with water is called hydrolysis. And when you put salt in water, it ionizes. It forms the ions. So you are able to see that, okay, this electrolyte is a substance of which aqueous solution contains ions. So it means when you have a salt in water, its aqueous solution will contain ions because the salt in water ionizes. So you are able to see that this electrolyte, there must be a salt, and that salt must be in water. Hence, we are saying it's an aqueous solution that contains ions. So a substance of which the aqueous solution contains ions, we call it the electrolyte. Or you can define the electrolyte as a substance that dissolves in water, the same thing that I'm still explaining. This substance is dissolved in water to give a solution that conducts electricity. You see now the importance of that salt dissolving in water. When the substance dissolves in water, it forms ions, and these ions definitely will help with the electricity conduction. So we are saying it's a substance that dissolves in water to give a solution that conducts electricity. So you can define it, the first part, which is the substance of which the aqueous solution contains ions, or a substance that dissolves in water to give a solution that conducts electricity. You can choose any of those two according to what you prefer, but definitely you can't go to that exam room without knowing what an electrolyte is. And then now we're going to look at the relation of current and potential difference. You see now, we're still talking about current and potential difference. So we have current here, which means as we've been talking about loss of electron, gaining of electrons. So you are able to see that as the electrons are flowing, there will be current. And if we're talking about current, we'll talk about the potential difference. We'll talk about the EMF. So there is expectation. You'll see as I go on, we'll be talking to the EMF of the cell. So we're saying you must be able to state the potential difference of a galvanic cell is related to the extent to which spontaneous reaction or spontaneous cell reaction has reached equilibrium. So there is equilibrium. You have done chemical equilibrium, and you know that at equilibrium, we're saying the rate of forward reaction is equal to the rate of reverse reaction. So there must be forward reaction and reverse reaction for us to reach equilibrium. So we'll be looking at that as well to say, in this case, we're having the forward reaction, we're having the reverse reaction, and what is happening at equilibrium. And we're saying we're going to state and use qualitative relationship between V cell, the EMF of the cell, and the concentration of product ions. Product ions. You know, for a reaction, if I can demonstrate for you, for a reaction to take place, let's say we're having this reaction, zinc and copper 2 plus, reacting to form zinc 2 plus copper. So in our reactants, we're having zinc and copper 2 plus. In our products, we're having zinc 2 plus and copper. So this statement is saying if we increase the concentration of the product ions, so when we increase zinc 2 plus, for example, on the product, you know what happens. If we are at equilibrium, the equilibrium will be disturbed. What happened is that when we increase the concentration of the product ions, the reverse reaction is favored. If reverse reaction is favored, you know the V of the cell will decrease, which is what we are saying here. But if we increase the concentration of the reactant ions, the copper 2 plus, if we increase this one, when this concentration increases, the EMF increases. When this concentration increases, the EMF decreases. So you got to have that appreciation of saying this EMF will depend on the concentration. As we increase the concentration of copper 2 plus or of the reactant ions, we're expecting the EMF to increase. As we increase the concentration of the product ions, we're expecting the EMF or our V of the cell to decrease. This is what our exam guideline talks to. And we are saying when we reach equilibrium, we are saying the V cell equals to 0. So at equilibrium, the EMF is 0, and we say the cell is flat. So we're going to look at that as well. And it's a question that is asked to say, what happens at equilibrium? You got to know that the V of the cell equals to 0 volts, and then we are able to move. I hope that has laid a nice foundation for you as we start. Now, we are going now as well to look at the processes and the redox reaction takes place in a galvanic cell. So here, remember, we talked about the electrolyte as a solution that have a substance that have been dissolved in water that gives rise to a solution that conducts electricity. So we are saying here as well, we're going to talk about the movement of ions. And then we're going to talk again about the direction of electrons. Where are the electrons flowing? So we're going to look at what is referred to as the external circuit, and what is referred to as the internal circuit. So you can see we're integrating what you know already in terms of electricity, that we have the internal circuit and the external circuit. So we'll be referring to that as well. We'll be focusing as well on the reaction that happens at the electrodes. Already I told you that this electrode at the anode, we said an oxidation taking place, and we said oxidation is loss of electrons. So loss of electron is oxidation, and this happens at the anode. And at the cathode, we said red cat. Remember, all this we are making you to remember that at the cathode, the reaction that takes place is a reduction, and reduction is gaining of electrons. So gaining of electrons is a reduction. Remember, you can use that Lioga, or you can use oil rig, as I said at the beginning, to say oxidation is loss of electrons and takes place at the anode, and then reduction is gaining of electrons and takes place at the cathode. So you must be able to know where gaining of electrons take place. It happens at the cathode, where loss of electrons take place at the anode. I know you are having a question to say, how will I know which substance is going to gain or lose electrons? Don't worry, that is the purpose of this lesson. When you finish this lesson, you must be able, when you are given two substances, to know which one will lose electrons, which one will gain electrons. And we talked about the internal circuit, where we have the salt bridge there. We're saying we must know the functions now of the salt bridge, and then the salt bridge as well. And you must be able to use what is called cell notation or cell diagrams to represent a galvanic cell. So you can represent a galvanic cell using what is called cell notation. So we're going to look at the cell notation, and we're saying when writing cell notation, the following convention should be used. Important. If you look in your table for A or for B, you will see that we are having the hydrogen plus half cell, and we are saying that is treated like any other. And if you look in your table, like I have my table with me here, you are able to see that this one, the hydrogen one, it has the EMF or E value, standard reduction potential of 0.00 volts. So you are able to see that is the hydrogen half cell. Now, and then we are saying when you write your cell notation, we are saying the first thing which is important, you will always look that outside you must have electrodes. Important. I want to emphasize that one at the beginning of this lesson, to say we need a solid, because a solid is a good conductor of electricity. Hence we are saying that we must have solids. And if we don't have a solid in the reactants, particles, or the product, we are going to use platinum. Remember, platinum is a good conductor of electricity, but now is inert. It doesn't disturb with the reaction. So we use either a graphite, which is carbon, or we use sulfur. We use platinum. I meant to say. So these two, we usually use them when we have, because they are inert electrodes, which means they are unreactive. They don't interfere with your reaction. You are just using them as the conductors if you don't have a conductor. Now, if you are having active electrodes, it means you are having two solids. The solids will be out in the outside of your reaction. It means here you'll have a solid, which one will be your reducing agent. If it's solid, for example, if it's zinc, it will be your zinc there, and then that is your solid. The zinc is solid, and then you are having the oxidized species. In this case, it will be zinc 2+. You are able to see that, and they are separated by the salt bridge in between them. Remember, you have the salt bridge. We'll be looking at the functions of the salt bridge to say what is the function of the salt bridge, and then that will the oxidized ions. In this case, it was copper 2+, forming copper. So you are able to see that if you have two solids, you will write your cell notation like that. So when you write cell notation, we are saying A, B, C. So you write the anode, you write the salt bridge, you write the cathode, and that's how you write your cell notation. But in case where you are having now some of the inactive electrodes, Like for example, when you are having, we're given here chlorine gas and Cl minus. Cl minus and chlorine gas is there in your table. I think if you check the table of standard reduction potential, you can look for chlorine, and then you can look as well for F2, which is the last one there in your table, I think, with the standard reduction potential of positive 2,87. And then you are having your Cl as well, Cl2, with a standard reduction potential of positive 1,36. Don't worry, we'll be talking to that. But the main thing I want to show is that your fluoride gas and your fluorine ion, your fluorine gas and your fluoride ion, it's important that you call it correctly, fluoride ion. Yeah, we have your fluorine gas and your fluoride ions, and then we're saying all of this. The fluorine gas is gas, is a gas. Fluoride ions is aqueous. You see, we don't have the solid there, hence we must be able to use platinum as a good conductor. So it means now the cathode, remember on the right we have a cathode. The cathode will be platinum when we don't have a solid cathode in terms of the reactants and the products that are being formed in terms of F2 and F minus. They are gas and aqueous, and it's important that you have that appreciation to say always when we don't have a solid, we're going to use platinum or carbon, which is our graphite, and then in this case we are using the metallic inert electrode, which is platinum. Remember, carbon is a non-metal, but it's a good conductor of electricity, so we can still use it to conduct the electricity. So we are saying in this case we're using the metallic one, because in the questions they can say which metallic inert electrode do we use when we don't have a solid electrode. You must be able to know that it is platinum, which is metallic. But if you say which one is non-metallic electrode that you can use when you are dealing with inert electrodes, you got to know that it must be carbon. But in this case, the metallic one is platinum. And most of the questions in question 8 were using this platinum. But don't cramp, always know that we can as well use graphite or carbon. So I think now you have the appreciation of the cell notation, and we'll still talk to it when we do go further in the lesson. But I felt that I must emphasize this one, because more especially when we are dealing with these inert electrodes, learners, they just write Cl minus and Cl2, F2 and F minus without the platinum, and the answer becomes wrong. So I'm emphasizing it so that we move together with that one. And I'm saying to you, you see that platinum is separated by a solid line. That solid line that you see there, that solid line, it shows that platinum and chlorine minus are in different phases. So we call it a phase boundary. So this shows that these two are in different phases, and chlorine minus and Cl2 are in different phases, hence we are still writing that solid line. So the solid line is a phase boundary. It shows that the substances have different phases. But in case where, for example, you are having, say, Fe3 plus, say, with Fe2 plus, you don't write a solid line, you write a comma like that, because that comma shows that Fe3 plus and Fe2 plus are in the same phase. So you got to have that. And definitely, you will definitely need platinum as your electrode there, because now you know that Fe3 plus and Fe2 plus are aqueous solution. So you will have seen that these positively charged ions or charged ions that we're having, they are in aqueous solutions. So if you have aqueous solutions for both Fe3 plus and Fe2 plus, you will still need platinum, which is now will act as your electrode, because you want it to be the one that will remember, we said these ions, they help with the conduction of electricity, but in terms of a conductor, in terms of the external circuit, you definitely need a solid. That's where you will connect to platinum or connecting to the other side. So that's what I wanted to emphasize, and I hope that helped you and you are ready to deal with the questions that relate to this topic. Now, this is still our exam guideline, the last part of our exam guideline, I promise you. We are saying now, you must be able to predict half cell in which reduction will take place. So, say, how am I going to know which one will undergo reduction, which one will undergo oxidation. Purpose of our lesson. When we leave here, you must be knowing how to determine which substance undergoes reduction, which substance undergoes oxidation. You must be able to write the overall cell reaction. You have seen, I've shown you the half cell reactions where I've shown you that with zinc, can lose electrons. Copper 2 plus ions can gain electrons at the cathode to form copper. And then I'm saying to you now, we must be able now to come to overall, where we come up with the overall cell reaction by combining. We must be able to combine these two, and that's what we are definitely going to do, and you will appreciate that important aspect of this. You must be able to calculate the EMF of the cell. EMF of the cell. End of the lesson. We don't have many calculations in terms of question 8. So this is one of the calculations that definitely you can't go to the exam room without knowing. So we will be looking at that. The formula is there in the data sheet. We'll go through it, how to calculate the EMF. And then we are going to use to look at the positive value. When we calculate the EMF of the cell, when the value is positive, it means that the reaction is spontaneous. So when you get the positive answer, it shows that the reaction is spontaneous. Remember, galvanic cell by its nature is a spontaneous reaction, which means there is no energy that is added because we are producing energy here. Remember we said energy convention, chemical energy to electrical energy. So this process is a spontaneous process, and we are saying this process is an exothermic process because energy is released. You have done exothermic when you're doing your rates of reactions and when you're doing your chemical equilibrium. So you must know that EMF of a cell, for galvanic cell, you expect it to be positive. What does positive mean? EMF mean? It means that the reaction is spontaneous. And when it's spontaneous, we're saying now these reactions, which are galvanic cells, they are exothermic in nature. And if you find a negative EMF, it will show that that cell is non-spontaneous, which is what we'll deal with when we are dealing with electrolysis, which is a non-spontaneous process. But for galvanic processes, we are saying galvanic cell is a cell that converts chemical energy to electrical energy. And because we are producing electrical energy, we are saying this is an exothermic reaction. And we are saying the EMF of this cell, we expect it to be positive because this is a spontaneous reaction. You know, spontaneous, it means the participant or the reactants are willing, are not forced. So whichever substance that is going to lose electrons, it won't be forced. It will give electrons because it wants to do so. Whichever substance is going to gain electrons, which we said is the oxidizing agent, is willing to gain electrons. Hence, the process is self-sustaining. Is able now. We are saying it is spontaneous, and because the EMF of the cell is positive, and the process is exothermic. And lastly, we're going to talk about the standard conditions. I know you know the standard conditions for chemical equilibrium. The standard the conditions that affect the chemical equilibrium. You remember those, which is your capital, which is your concentration, your pressure, and your temperature. These are the factors that affect chemical equilibrium. In this case, it is still your Cape Town, but we need values. You see, when we're dealing with chemical equilibrium, when you say what are the factors affecting chemical equilibrium, you will simply say concentration, pressure, and temperature. But here in galvanic cell, when we say what are the standard conditions, you are going to take a deep breath and relax and say, here we're talking about initial concentration. That initial is very much important, that this concentration is not any concentration. It is the initial concentration. Initial concentration under standard conditions must be 1 mole per cubic decimeter. So those are 3 conditions. The first one it is initial. It's not concentration, it's initial concentration. Must be 1 mole per cubic decimeter. You will understand as we go on with the lesson why initially the concentration is 1 mole per cubic decimeter, why the concentration changes as the reaction proceeds. So that is the first condition. The second one is temperature. I always say you will write pressure as the third condition. Why, learners? I advise you to do so because pressure affects only gases. Remember, when you were dealing with factors affecting equilibrium, you talked about that to say pressure affects only gases. Even here under this topic, pressure affects only gases. It means we must be gases involved in the galvanic cell for us to talk about pressure. Now, in terms of temperature, we're saying the temperature is 25 degrees Celsius. Don't make a mistake. If you check in your data sheet, you will see that the temperature there is given as standard temperature as 273 kelvins. But for galvanic cell, the temperature is 298, not 273. So you must be able to, how to convert degrees Celsius to kelvins. You must be able to add the 25 to the 273. That is in your data sheet. So it means now standard temperature is 298 kelvins or 25 degrees Celsius. You can just stay with 25 degrees Celsius, which is our room temperature. And our pressure is 101. At least this one, standard pressure is given as 101.3 kilopascals, even in your data sheet. So you can go to the data sheet and look for pressure. It's 101.3 kilopascals. And we're saying it only applies when we have gases. And then if you don't want to talk about kilopascals, you can just say 1 atm. I know some of you like the ATM. 1 atm, we stand for 1 atmospheric pressure. So you see, I've outlined these standard conditions for this reaction. So we're saying the values that you see on the table of standard reduction potential, those values are based on these conditions. If this condition changes, everything changes. So it's important that whatever that we are doing, we do it under standard condition, which is initial concentration of 1 mole per cubic decimeter, temperature of 25 degrees Celsius, pressure of 101.3 kilopascals or 1 atm. And then we are saying you can't just say concentration, pressure, and temperature. You must give us the values to say initial concentration 1 mole per cubic decimeter, temperature 25 degrees Celsius or 298 kelvins, pressure 101.3 kilopascals or 1 atm. I hope we're moving. I think I've explained that the best. You'll never forget that. Come exams, you are ready. When you say write down 2 or 3 standard conditions, you are able to write them. I told you that if we say write down 2, you'll write concentration and temperature first. Then pressure is number 3 because it only affects when we have gases. If you have no gases, you will only have 2 factors that affect, or 2 standard conditions. I hope we are together. The last bullet there says you must be able to, second from last, you must be able to talk to describe the standard hydrogen electrode. The standard hydrogen, I've shown you hydrogen there as a reference electrode to say it means for us to get all the other values, we had this standard hydrogen electrode, which is 0.00. So you can see that when you go on top of the table in table 4b, you have your negative values. When you're going downwards, you have your positive values, and we'll talk about that. And then we are saying now that's what you must be able to have understanding. Now, this work started in grade 10. So we are saying the foundation was there. Even before grade 10, I know you were doing electrolysis, grade 8 and 9, NS and all that. So you had you talk to these processes, but now we are taking you back to say this doesn't start in grade 12. NSC, I'm always emphasizing, is a 3-year course that starts in grade 10. Now you are in the final year, which is grade 12. And then at the end of this year, at the beginning of next year, you'll be able to receive your certificate for National Senior Certificate. So you are in the final year. But let's go to your first year, which was grade 10. Hence, we are saying, don't even throw away your books for grade 10. You can always go back and refer. Now, You talked in grade 10 about pure substances, which are your elements and your compounds. So in this case, in terms of galvanic cells or electrochemistry, when we say substance, we'll be talking about your elements. You see them as they appear in the periodic table, your compounds when you have joined them together, and your ions. So when I say substance, it's either I'm talking about elements, compounds, or ions. So all the time, remember that substances, when you say a substance, you are referring to those three. And you know that the elements, we said they cannot be broken down. They cannot, those ones in the predictable, we said you can't break them down into simpler substances by chemical means. But the compound, we're saying here, these are substances that consist of two or more elements chemically bonded in a specific ratio. So you know the compounds, and then you have done as well in grade 10 the naming compounds of, you remember the table of negative and positive ions. I think those are very much important for this particular lesson, because you will remember your positives like your metals Ag plus and chlorine minus being given as AgCl, all that, your copper sulfate, your zinc sulfate, zinc 2 plus and SO4 2 minus. When you bring them together, they give you zinc sulfate. So it's important there, because when you see zinc sulfate, a science learner doesn't see sees zinc 2 plus and SO4 2 minus, because you are seeing that zinc, it has an oxidation number of 2. So those oxidation numbers, when you're dealing with these positive and negative ions, very much important. In fact, the whole of this lesson topic is based on those ions, and you got to remember them, all of them, even the nitrates as well. Remember, you've done the nitrates, the chlorides, all that. So I'm saying to you, go to your grade 10 book and have a look there, and just to remind yourself so that you are more comfortable with what we are doing. And we are saying, when you go to the predictable, we're having the charge of simple ions that can generally be deduced from the group number. Remember, you have group, some will say group 1, Roman figure 1, group 2, group 3, group 4, group 5, group 6, group 7, and group 8. Yes, even your predictable is written like that. It's either group 1, 2, 13, 14, 15, 16, 17, 18, or 1, 2, 3, 4, 5, 6, 7, up to 8. And we're saying group 8 are fully filled. So we don't expect them to have any oxidation numbers. Their oxidation number is 0. And the rest of these groups, they will want to be like group 8. Hence, we're having these reactions that are taking place, because they want to lose those valence electrons. These ones, the metals want to lose the valence electrons so that they can be fully filled, and then the non-metals want to gain electrons so that they can be fully filled as well. Hence, we're saying the group 1 element, which is your metals now. Group 1 is your alkali metals, where you are having your LINAC there, your lithium, sodium, and potassium. So those metals, they have ability to lose 1 electrons. So their charge is +1, because lithium can only lose 1 electron. It cannot lose more than 1 electron. So when you see lithium, you know that it can only lose 1 electron. Sodium, the same, say group 1, they have a valence of 1. Because of that valence of 1, they have 1 electron in the outermost energy level, and they can only lose electrons. And then potassium, for example, it can only lose 1 electron. So these are group 1 elements. You have your group 2, when you are having your magnesium, your calcium, those ones, they can lose 2 electrons. So I'm saying, as to how many electrons the metal will lose or gain, already you know. And then you will have seen that I'm mostly referring to metals as being the ones that will lose the electrons in the language there. The main thing is that, remember, when we were doing metallic bonding in grade 10, you said that the electrons in metals, those electrons are delocalized. So the electrons are not embedded within the structure; they're delocalized around the metal ions. So you are able to see that these electrons, it's easy for metals to lose electrons, because the electrons in the metals, those valence electrons of 1, 2, 3, they are not firmly bound. They're just holding loosely to the metal. So it's easy for metals to lose electrons. So when you are having a metal and a non-metal in a galvanic cell, definitely you will know that a metal will lose electron and a non-metal will gain electrons. Hence, we are referring to metals as +1, because for that +1 is a charge of 1. And that charge of 1, remember, we're referring to them as cation ions, which are positive ions. So we're saying group 1 elements will form 1 charge. Cations of group 2 elements will be 2 plus. Group 13 or group 3. Group 13 is where we are having our aluminium. So you will know that aluminium can lose 3 electrons. But now it depends it's reacting with what, because sometimes you'll have a metal, and then in that case we're going to look at the standard reduction potential to say who has more potential to gain electrons between the two metals. But if it's a metal and a non-metal, it becomes easier for you to know that the metal will lose electron, the non-metal will gain. But there will be cases, you'll see when we start with the examples, there will be cases where you are having a positive, a metal and a metal. So we got to know which one will lose. But when you have a metal and a non-metal, definitely a metal will lose electrons and non-metal will gain electrons. So aluminium in group 13 there. Group 14, where we have our carbon. Hence our carbon, when we were doing organic chemistry, we were focusing on the carbon. We said ±4 is forming. We said this carbon will nicely, it can form the four bonds around it, because it's in group 4, and we said it's sharing covalent bonding, it's sharing electrons. So you see, the metals, they have ability to lose, but when it comes to carbon, it can share electrons. Hence we're saying ±4. And then the non-metals, they are more likely to gain electrons. Why? Because the electrons are closely bound, firmly bound to the structure. It's not easy to remove them. That's why most of the time you will see when we do electrolysis, we will use electricity to force the non-metals like your chlorine minus to lose electrons. So for them to lose electrons, it cannot be a spontaneous process. It will be a non-spontaneous process. But in a spontaneous process, a metal will lose electron, a non-metal will gain electrons. So hope you are with me. And then interested as well, where we have our oxygen, then group 16 or group 6, oxygen was saying it can gain up to 2 electrons. And then chlorine, our halogens now, we are saying they have a valence of -1, which means they can gain 1 electron. So I'm thinking that now you see the importance of this information that you have learned in grade 10. Now the last part, you have done metals and materials, you have done metals, and you said metals are good conductors of electricity. Why? Because they have a valence of 1 and 3, which is what I was explaining from, you see, when we have our lithium, our magnesium, our aluminium. As we move from the left of the predictable to the right, you can see that those metals are more likely to lose electrons. Why is it like that? Because these valence electrons are very loosely bound, so it's easy for metals to lose electrons. And then you have done the non-metals, still in grade 10, and you said they contain the valence of 4 to 7 electrons, and we are saying these electrons are firmly bound, so it's not easy to remove these electrons from non-metals. And then hence we are saying now we call them insulators. They are not good conductors because they cannot make the electrons to flow. They cannot lose those electrons. Hence, the non-metals are insulators. The metals are good conductors because they can easily lose electrons because the electrons are loosely bound. But when it comes to non-metals, we're saying those electrons are firmly bound, so they cannot conduct electricity. But we have exception. So you don't say always non-metals don't conduct electricity, because there is an exception of this special non-metal that conduct electricity is called graphite, carbon. I told you about this one. To say carbon is a non-metal of special kind because it's a non-metal, but it can conduct electricity. This is the graphite that is used in the pencil. So the pencils that we are having, they have carbon there. and that carbon we're saying is a good conductor of electricity. You'll see when you do electrolysis, and then you can even look at the experiment. You can even use the pencils as you do the experiments to show that they are good conductors of electricity. So this is what you have done in grade 10. Now let's look at your grade 11. In grade 11, you have done your oxidation, reduction, your anode, all those. Remember, oil rig, we said oxidation is loss of electron, or I said LEO, which is loss of electron, is oxidation. Gaining of electrons is reduction. So this is your definitions. But remember, I said when you define oxidation and reduction, it will depend. We'll say in terms of electron transfer, you'll say loss of electron, gaining of electrons. But we can say in terms of oxidation numbers, you are able, oxidation is increase in oxidation number. Reduction is a decrease in oxidation number. So you know how to define oxidation and reduction. Now, the anode, we said, is the electrode. Remember I was telling you about the suffix there. To say anode is the electrode. It is the electrode where oxidation takes place. So it is the electrode where oxidation takes place, and then that is the anode, is the electrode where oxidation takes place. And then the cathode is the electrode where reduction takes place. I didn't say the cathode undergoes reduction, but I said where the cathode is, that's where reduction will take place. And remember, reduction is gaining of electrons. And then the reducing agent, I usually use this mnemonic to say Leo, Ra, and then say Ge, Roa, so that you always remember this. I find it very easy for you to remember this, to say, okay, loss of electron is oxidation, and this substance that undergoes that loses electrons, we call it a reducing agent. So what am I saying? I'm saying if we have zinc, for example, losing electrons to form zinc 2 plus 2 electrons. So we are saying this is loss of electron. We call this oxidation. This reaction is called oxidation. And zinc, a substance, remember I said substance is your element, is your compound, is your ions. So we are moving together now. What is a reducing agent? We are saying it's a substance that undergoes oxidation, or a substance that undergoes loss of electrons, or a substance that is oxidized. So you call it like that, you know how to answer those questions. Now, we have a substance that gains electrons. That one, I said, can be copper 2 plus. Gaining electrons to form copper. And I'm saying now, this copper 2 plus is gaining electrons, is undergoing reduction from 2 plus to 0. You can see the oxidation numbers is decreasing because we said reduction is the decrease in oxidation number, remember. And then we are saying now this is gaining of electrons. We call this reaction reduction. And we are saying what is the oxidizing agent? It's a substance which is copper 2 plus. Remember, our substances are always in the reactant side. So we are saying is the substance that undergoes reduction, which is copper 2 plus. Who undergoes reduction is copper 2 plus. It's reduced to copper. So a substance that undergoes reduction, we call it the oxidizing agent. Or you can say oxidizing agent is a substance that gains electrons, or a substance that is reduced. So you are able to see that is your oxidizing agent. And definitely you will get all those, and when you get one or two of these definitions, you are able to remember at all times. So we talked about now the anode. The anode, we said, is where electrode where oxidation takes place. You can see oxidation is this one. So this is our anode. Zinc is our anode. And what is a cathode? We said a cathode, red cat, is an electrode where reduction takes place. So you know that this is a cathode. So you are able to determine all that. And we said anode is an electrode where oxidation takes place. Cathode is an electrode where reduction takes place. And ox and red cat for you to always remember. So we have talked about reducing agent and oxidizing agent. We are done. And then oxidation numbers, grade 11 as well. You have done oxidation numbers, very much important. I'm going to give you an activity now so that you are able now to look at your knowledge of what you have done. And then we have electrolysis and then we have electrolysis of copper chloride, which is what we'll do when we deal with the electrolysis, which will be our next lesson. Now, oxidation numbers, I will just remind you, more especially the most important rules, which we put the most important rules first. For this one, we're saying a neutral compound oxidation number always add up to 0. So, for example, when you're given CO2, you know carbon, we said is -2. Remember that charge, those charges I was showing you, group 16 -2, group 17 -1, group 15 -3, group 14 or group 4 plus or minus 4, group 1 plus 1, group 2 plus 2, group 3 plus 3. Those things always remember. To say, okay, oxygen is -2, group 16, and then -2 times 2 is -4, which means the oxidation number of carbon is +4. Because when we add the oxidation numbers, they must always add up to 0. So when you say 4 minus 4 is 0. So hence CO2 is neutral. Always the oxidation number is to 0. Now, in an ion, the oxidation numbers add up to the charge on the ion. For example, when we are having SO4 2 minus. So you are saying your answer must be -2. So what do you do here? You are saying for oxygen is -2. What is -2 times 8? 4 is -8. So you can see that this is -8 for oxygen. And for sulfur, it must be what? You need a number now. I can just put an X there. For sulfur, then you take -8 that side, X equals to +6. So you know that this must be 6, so that our answer is -2, because you know that 6 minus 8 is -2. So revisit all those oxidation numbers, and then you are able to see. And we are saying free elements have an oxidation number of 0. All the free elements. If sodium is alone, iron is alone, you know the oxidation number must be 0. And the oxidation number of a diatomic molecule, the oxidation number of a diatomic molecules, for example, your H2, your O2, you will treat them as free elements as well, because their oxidation number is 0. So 0 is for free elements and for diatomic molecules. When a molecule is with itself, bonded to itself, you are saying those are diatomic molecules. You know all your gases, those gases that you are having, your hydrogen gas, your oxygen gas, your Cl2, your F2, your Br2, all those, they will have a oxidation number of 0 because they are diatomic molecules. And then you are able to know that the group 1, we said, is +1, group 2 is +2, group 3 is +3, and then hydrogen with non-metals, you know, it will be +1. Hydrogen with boron is only exception there. And hydrogen, when it's with boron, you will have something of that nature, or when hydrogen is with a metal, then it will take -1. Those are small exceptions. For example, oxygen is -2, but not always. When depending who the oxygen or which molecule that the oxygen is dealing with. For example, in H2O2, remember hydrogen is +1 times 2, it will be that one, then oxygen will take a -1. So it's only those few exceptions that we don't really ask you about them. The main thing that you got to know, the group 17 -1, group 16 -2, group 15 -3. So I hope you will always revisit the oxidation numbers, because you can be able to answer questions here based on oxidation numbers. And this is your baseline activity based on the previous grade 11 examination. That is for you to appreciate what we have done in grade 11 as well. To say the reaction between permanganate ion, MnO4, and hydrogen sulfide is given below. So you have MnO4 plus hydrogen gas forming H2S, Mn2 plus sulfur forming water. And then the questions define reduction in terms of oxidation numbers. You will be able to do that. I will give you time to answer these questions, just 10 minutes. In 10 minutes time, you must be done. And then you must be able to determine the oxidation number of manganese, to write down the formula for the substance that undergoes oxidation. Explain the answer to question 1.3. You must be able to write down the formula of the oxidizing agent. You must be able to write down the oxidation half reaction. You must be able to use the ion electron method and write down the balanced net ionic equation. So I'm giving you 10 minutes. It's 23 past. So in 10 minutes time, I'm going to come, then we do the solution. And this is your foundation for this topic. So without any wasting of time, I'm giving you that 10 minutes. Answer this question. Remember, you have the table there for A and for B that you can always refer to them. Thank you very much. See you in 10 minutes time. Welcome back. Hoping you enjoyed the activity. Remember, the first question was define reduction in terms of oxidation number. So reduction, we said, is a decrease in oxidation number. So that is your 2 marks for writing that. The second question, which was 1.2, was determine the oxidation number of manganese in permanganate ion. So the expectation is that you knew that oxygen is -2. You multiply by 4, you get -8. And then that will give -8 plus 7. You want the final charge is -1. So you know that the answer must be -1. So if we have -8, what number do we need? You are able to see that Mn will be +7, and then you are able to get your answer there, which is Mn is +7 or Mn 7 plus. That is the oxidation number of manganese. The next question was on determining. Write down the formula of the substance that undergoes oxidation. So you are able now to check. Remember, oxidation, we are saying that now is a loss of electrons. So you can see Mn, we said it was +7. This side is +2. You can see that it shows that it has gained electrons, which is now reduction. So you will see there that what has changed is that you had hydrogen here, which is +1. Sulfur would be -2. And then from -2 for sulfur to 0, you are able to see that indeed it is H2S or S2 minus that undergoes oxidation. It has increased from -2 to 0, which is this question that says explain the answer in 1.3. We are able now to say oxidation number of sulfur increases from -2 to 0. And then the next question was on 1.5. It was write down the formula of the oxidizing agent. Remember, oxidizing agent, we talked about Mn2 plus. Remember, we said gaining of electrons is reduction, which is the oxidizing agent that is reduced. So oxidizing agent is a substance that undergoes reduction, which in this case it was Mn04 minus or Mn7 plus that became Mn2 plus. So you can see that it has gained electrons. The oxidation number has decreased. And then 1.6, write down the oxidation half reaction, which is loss of electrons. Loss of electrons, you indicated is your H2S there, then your H2S will lose electrons in that way, which gives you the sulfur plus 2 hydrogens plus 2 electrons. And then they use the ion electron method and write down the balanced net ionic equation. This is what you are expecting even as you deal with your net reaction, even here in grade 12. So you will write your oxidation half reaction and your reduction half reaction. From there, you must be able to balance everything. Your hydrogens, your electrons must be balanced of these two. Hence, you can see we have 2 electrons here and 5 electrons. Hence, you multiply 2 by 5 and 5 by 2. And when you do the multiplication, you multiply the entire H2S reaction, oxidation half reaction, you multiply the entire of it by 5. So it will be 5 H2S, it will be 5S, it will be 10 electrons. When you multiply the second one by 2, you will multiply by 2, by 2, 2, 2, 2, 2, and then you are able to get that. And what you do, what you have on the left there, the first thing you will do, you will cancel the electrons because they will be equal. Remember, you have multiplied this entire reaction by 5. You'll multiply this entire reaction by 2. By 2, everything you multiply by 2. And then when you have done that, what you will do, you will now cancel the electrons because there will be 10 both sides. They are equal. And then you are able now to do your addition. And then you add your 10 hydrogen plus and your 16 there. And then 16 minus 10, you're able to get 6. So you're able to, what is on the left, you write on the left. What is on the right, you write on the right. And you will get another mark for writing the overall cell reaction or the net ionic equation. And the last mark is for balancing. When everything is balanced like that, you get 3 marks. So I'm hoping you will do that. And we're going to be doing that a lot as we deal with questions here in grade 12. Remember, we said redox is loss of electrons and reduction is gaining of electrons. And we're saying this happens in real life. The redox reactions, they do take place during rusting. I think you have seen your iron nails that are now losing electrons when oxygen takes the electrons from iron to form iron oxide, which is commonly known as rusting. You see that rusting. Now you know that when you see your iron there being like that, it has rust, which means it has oxygen was able to take the electrons, or iron lost the electrons there and is rusting in the process. Now the other question is to say, is this a redox reaction? And then you have to check. Remember, you are using the oxidation numbers to say, oh, when it's alone is 0 oxidation. Hydrogen is group 1 is positive 1. Chlorine group 17 minus 1. So let's go this side. You have magnesium Cl2, you know chlorine is minus 1. When you multiply that by 2, you get minus 2, which means magnesium is positive 2. Anyway, you know that magnesium, when it loses electrons, is in group 2. The charge must be plus 2. So those charges are able to make you remember. Hydrogen and hydrogen, you treat it as a free electron, as a free atom, so it will be 0. So you can see that we have magnesium that is oxidized to magnesium 2 plus. We have hydrogen from positive 1 to 0. So you can be able to see that this indeed is a redox reaction. Why? Because we are having loss of electron by magnesium that forms like that, and then this is oxidation, and then you are having as well your hydrogen there, your hydrogen ion there, that is gaining an electron to form hydrogen. So it will be 2 hydrogen just to balance it, gaining 2 electrons to form your hydrogen gas. So you're able to see that this is a redox reaction because of that. So this is a redox reaction because we have oxidation, loss of electrons, and gaining of electrons, which is reduction. And so we're saying this is a redox reaction. So you can see the importance of redox of oxidation numbers. Now we're saying a galvanic cell, the other name that we use for galvanic cell, we call it a voltaic cell. And already we said it converts chemical energy to electrical energy. And we're saying this is a spontaneous reaction that takes place. It can take place in the same beaker. I want you to have that when we start the lesson so that you have understanding that this reaction can take place in the same beaker, and we refer to the process as direct electron transfer. So it depends. If we have correct reactants, galvanic cell, this reaction can take place in one beaker, like I've shown you there, where we are having zinc and copper sulfate. So you're having copper sulfate as your solution there, and you are having zinc. When you do that, you have correct reactants here, which is zinc. Remember, I want to emphasize this as we start. When you look at table 4b or 4a, you will see that on the left, you are having oxidizing agents. On the left of the table is oxidizing agent. On the right is reducing agent. And if you check your zinc cell is given as zinc 2 plus 2 electrons forming zinc. Your copper is given as copper 2 plus 2 electrons forming copper. Is given like that. And then that's what now we're looking at on the left of the table 4b or table 4a. I usually use table 4b for galvanic cells. It just makes it much easier for me. But you just have to know that the tables serve the same purpose, but you have to use the table that makes it easier for you to answer the questions. And if you check on the table, you will see that on the left there we have oxidizing agent. On the right we have reducing agent. So what happens is that the arrow for oxidizing agent is downwards that side. For the reducing agent, the arrow is upward. So what happens is that the reaction is always between a strong reducing agent and a strong oxidizing agent. So the arrow is showing you which one is strong. So as you go downwards on table 4b, you find strong oxidizing agents on the left. So it means the reaction is between copper 2 plus. On the right, strong reducing agent is zinc. And we are saying these two, when they react together, they will have a spontaneous reaction. So we are able to know that when you have zinc and copper 2 plus, zinc can lose electrons and copper 2 plus can gain electrons. And we call that direct electron transfer. But now, in order for us to show this process, nicely. Hence, we therefore separate the two half fractions by placing them in separate beakers. You will see most of the questions, you will find them in two different beakers. But we're saying the reaction can as well take place in one. So don't have that problem of saying, the main thing is that this is a spontaneous reaction. You can see we don't have any power source to show that this is self-sustaining. The reaction itself is able now to produce or to convert chemical energy to electrical energy. And then we're saying you can place them this in the separate beakers and connect them by a salt bridge, and electrons will move in the external circuit, which is what we're definitely going to do now as we conclude our lesson. To say the components of a galvanic cell, we're having an external circuit. You can see we're having the voltmeter and the conducting wires. And you can see that the conducting wires are connected to the electrode, and we said they must always be solid, these ones, so that they can conduct electricity. And we said if we don't have a solid, we'll use platinum or graphite because those are inert electrodes. So the two electrodes, one is the anode and the other one is the cathode. Remember anode, we said that's where oxidation occurs. Cathode, we said that's where reduction occurs. And we were saying we have two beakers consist of electrolytes. So here, the blue you see there is your electrolytes here, which we said these are substance that has been dissolved in water in to give solution that conducts electricity. So this is the solution that conducts electricity, which is our electrolyte. And we have a salt bridge, which is your internal circuit, internal circuit there. So you're able to see how a galvanic cell looks like. And we were saying in the external circuit, a conductor joins the anode and the cathode. You can see that is our conductor that joins them. And then electrons always move from anode, from the negative electrode, which is the anode, to the positive electrode, which is the cathode. So the electrons, remember we said loss of electron is oxidation on N-ox. At the anode, that's where oxidation takes place. So you know anode is the electrode where oxidation takes place. Cathode is the electrode where reduction takes place. And we're saying at the two electrodes, anode is the electrode where oxidation takes place. I already talked about that. And there we are having stronger reducing agent. At the anode, we have a stronger reducing agent. At the cathode is where reduction takes place. And at the cathode, we have a stronger oxidizing agent. So you are able to know that always it's an electrode inside the ions. Metal, it's a metal inside the metal ions, and the other metal inside the metal ions. And we are saying these ions, and then we are saying on the other side, we have the oxidizing agent. On the cathode, we have the oxidizing agent. On the anode, we have the reducing agent. Now, the salt bridge. We're saying the salt bridge is very important because it joins the two beakers there, the two fractions. And we're saying the function is of a salt bridge is to complete the circuit, which means it serves as a switch. Without the salt bridge, there is no, the circuit is incomplete. And we're saying it keeps the two electrolytes in the two half cells separate so that the two do not mix, and it allows the movement of ions between electrolytes to ensure electrical neutrality. So you see there are two main functions of a salt bridge, which is to complete the circuit and to maintain electrical neutrality. How does it do that? It allows the movement of ions. And I want you to have an understanding to say the cation ions, the positive ions will go to the anode, the negative ions, the N ions will go to the anode from the salt bridge. So in the salt bridge, we're expecting that we'll have a salt, and we'll have cation ions and N ions. Now, just to emphasize that when we have the zinc electrode, it must be in the zinc ions there. The electrolyte must be heavy, must be zinc. So it means zinc will be in zinc 2+. But now, some of the time we hide the zinc 2+ by writing as zinc sulfate. Hence, the oxidation number will remind you that SO4 is a 2-, which means zinc is a 2+. The same with copper 2+, we can write it as copper sulfate. You know that this is copper 2+ and SO4 2-, and we're interested on the copper 2+. So you got to know that on the anode side, we're going to have the zinc there. And then on the cathode side, we're going to have copper that side. Why is it like that? Because when I showed you on the table to say zinc is at the top of the table there, where we have stronger reducing agent. Remember, we're saying both zinc and copper on the right of your table 4b, both of them are reducing agent. But what differs is the strength of reducing agent. The same we're saying zinc 2 plus and copper 2 plus on your left there, they are both oxidizing agent. But what differs is the strength. Which one is stronger? We're saying as you go down, you find the stronger oxidizing agent, meaning copper 2 plus is a stronger oxidizing agent. Zinc is a stronger reducing agent, and the reaction is always between a stronger reducing agent and stronger oxidizing agent. So the ones that are by the side of the arrow, where the arrow is pointing, those are the ones that are our reactants. So in this case, our reactants will be zinc, that will reverse. It means zinc will lose electrons because it's a reactant. Zinc is a reactant, and copper 2 plus is a reactant, which means copper 2 plus will gain electrons. And then you are able to see that those are the half reactions. So reducing agent there in the anode, we know that is loss of electrons is oxidation, where we find our reducing agent that is oxidized. And in the cathode, we have gaining of electrons that undergoes reduction, which is our oxidizing agent, which is reduced. So you are able to see that. We have talked about the issue of the cell notation to say it's always A, P, which is the salt bridge, C, which is the cathode. So always you'll write in the anode, we have zinc solid forming zinc 2 plus, which is what we are having the anode. They are separated by the salt bridge. Remember, we said salt bridge has two functions: to complete the circuit and to maintain electrical neutrality through the movement of ions. Cations to the cathode, anions to the anode, in order for it to maintain neutrality. So you are able to get that. And then this is now a demonstration. You can see zinc loses electrons. They move from the anode to the copper side. But the electrons, when they come this side, they are not reacting with copper. They are reacting with copper 2 plus. So you got to have that understanding that the electrons are reacting with copper 2 plus. So you can see zinc, when it loses electrons, it becomes zinc 2 plus. So you can see the two electrons are going in the external circuit. The electrons are moving like that in that direction. That is the direction of the movement of your electrons. They move, but they leave here zinc 2 plus, which means there are two things that are happening here. When the zinc loses electrons, the electrolyte, which is the a solution of zinc 2 plus, increases. So in this case, the zinc 2 plus concentration increases as zinc loses electrons because it's forming zinc 2 plus. The zinc itself will decrease in mass. Zinc will decrease in mass because it's losing electrons. When you come to the cathode side, when the electrons come this side, they are reacting with copper 2 plus. So we're expecting that this solution this side, concentration, it won't be 1 mole per cubic decimeter forever because it's busy decreasing. When the copper 2 plus gains electrons, you can see the electrons, the copper 2 plus gains electrons to form copper. So this one will increase in mass, but the concentration of the electrolyte will decrease. So you can see we have increasing concentration on the anode and decreasing concentration of the electrolyte in there or on the cathode side. So you are able to see that the physical change is that the mass of zinc decreases. The physical change this side is that the mass of copper increases because copper 2 plus gains electrons to form copper. So I hope you are able to see that. On the salt bridge, we have a salt there. In this case, they said K plus potassium chloride. You are able to see that the potassium now K plus to the cathode, which means K plus will move that side, the Cl minus will come this side. Why? To maintain electrical neutrality. And we are saying this salt bridge, it serves as a switch there. We are saying that it is there to complete the circuit, which means if I remove the salt bridge, the cell won't be functional. So I hope you get that and you are able to see what that does. When it comes to calculation of the EMF, remember now we're having the cathode and the anode. I've shown you with our zinc 2 plus 2 electrons. We said it forms zinc, and then we had our copper 2 plus 2 electrons. They are written like that on table 4b, and then that forms copper. And the standard reduction potential for this one is negative 0.76 volts, and for the cathode that side 0.34. So you're able to see that A, and C. So you're able to see that the first one is our anode, the second one is our cathode. On the table, the one that you find first on the table is your anode, the one that comes second will be your cathode. So you're able to see that if you were to substitute there, for the cathode, you'll substitute 0.34 minus, for the anode is negative 0.76. Don't forget to write the negative of the formula there. And when you get that, you get your 1.1 volts. We said the answer must be positive because this reaction is spontaneous. The reaction is spontaneous and is exothermic, is producing electrical energy. So this is exothermic, which is your reaction. So you are able now to know that that's how you are moving in terms of it. And then we're able now to say, I just wanted here on this slide to explain the table and its meaning. To say, if you look now, already I've told you that on the table 4b, as we move down, we're finding the stronger oxidizing agent. Hence, we said where copper 2 plus was, which is down there, and zinc 2 plus was up, and then we say this copper 2 plus is a stronger oxidizing agent. And if you check on the right of your table, where you are having your zinc and your copper, we're saying as you go up, you are getting the strength of reducing agent increases. So hence the reaction will be between zinc, which is a stronger reducing agent, and copper 2 plus, which is a stronger oxidizing agent. So the reaction is between that. But I'm teaching you as well a skill here to say it's always two reducing agents on the right, two oxidizing agents on the right, but the stronger ones are the ones that win the war. So we're saying in this case copper 2 plus is a stronger oxidizing agent than zinc 2 plus, so it will be a reactant. Zinc is a stronger reducing agent than copper, it will be a reactant as well. Hence in our reaction we'll have zinc reacting with copper 2 plus to form zinc 2 plus plus copper. So you're able to see how we came to that overall cell reaction. And hence these arrows are showing you that oxidizing reducing agent, they go backward, the reaction is reversed. Hence when you write the zinc afresh cell, it will be reversed from zinc. You start with zinc, you reverse it to zinc 2 plus 2 electrons. When you come to copper 2 plus, you write it as is. Remember, as you write the half reactions, you are showing only one arrow, because these are half reactions. And the overall, we're saying reactants, you first check the electrons. When they are balanced, you cancel the electrons. And what is on the left is zinc and copper 2 plus, which is our stronger reducing agent and stronger oxidizing agent. They are able to form zinc 2 plus copper. So those are able to help us in terms of that. I hope this has helped you in understanding the table. Just wanted to show you the table, but I want us to deal with activities now as we finish our lesson, to say which one of the following statements regarding the anode of a standard galvanic cell in operation is correct. So always underline correct, because sometimes you'll say which one is incorrect. So you got to be able to see that the anode accepts electrons. Remember, it undergoes oxidation, is where oxidation occurs, which means in the anode there is loss of electrons, so that cannot be correct. The mass of the anode decreases. I told you that one, to say as the anode loses electrons, then definitely the mass will decrease. So that will be your 2 marks, your correct answer. If we look at 1.2, it's saying consider the reaction represented by the following equation. Which one of the following represent oxidizing agent in the above reaction? Remember, we said the reaction is always between stronger oxidizing agent and stronger reducing agent. And oxidizing agents are these ones that are positive, and then mostly positive. In this case, it's Ag plus, and copper will be your reducing agent. So stronger reducing agent plus stronger oxidizing agent, they react on the reactant side. And then you are able to see Ag plus as your oxidizing agent. Activity 1.3, it was in the electrochemical cell. The letters X and Y represent 2 metal electrodes. So we're having 2 metal electrodes, X and Y. When the cell is functioning, electrode X gains mass. So you know that the one that increases in mass is in the cathode, because there is gaining of electrons. So you can see that in that case, it means that we're losing electrons from Y to form this one, which means Y is losing electrons to form Y plus an electron. And on the X side, it means we're having X plus because we gain electrons in the cathode to form X. And if you can check the cell notation, we said we always start from anode to salt bridge to cathode. So you're able to see that your anode is your Y, forming Y plus, and you have the salt bridge, you have X plus forming your X. And then you can indicate as well whether it's solid and aqueous. Remember, your Y and X are solid, and then you are able to see that A is the correct answer in terms of 1.3. And then questions can be asked in this way, where you are given the half cell reaction, the cell notation. You got to always remember A, B, C. So you have, this must be your anode, this must be your salt bridge, this must be your cathode. And the other thing that I wanted to emphasize is that you can as well show for your aqueous solution, you must show that this happens at initial concentration of 1 mole per cubic decimeter. Will I be penalized? So far, penalizing for not writing 1 mole, we accept, but the correct answer will be the one that shows the concentration of the electrolyte, which is 1 mole per cubic decimeter, as we talked about that. So I wanted to understand, and some of the questions, you will get them in this way, where you are given the cell itself, and then you are able to be asked questions in which electrode does oxidation occurs. We've done this already. You know that oxidation, we said, is our zinc, because zinc is a stronger reducing agent. Remember on the table, stronger reducing agent will be obviously undergo oxidation. And in terms of this one, copper 2 plus is gaining electrons. Definitely this one must be a stronger oxidizing agent. So the reactant is a stronger reducing agent, and we know the reducing agent are on the left of the table, and the stronger oxidizing agent. So you are able to answer those questions. In which electrodes does the reduction occurs? And then you know that reduction is gaining of electrons. You see that is in the copper half cell. A reason is that copper 2 plus is a stronger reducing agent than zinc 2 plus. So those always helps you, and you can answer all the questions that you come across. What happened to the mass of the zinc? Remember, zinc is in the anode, and we said anode will decrease in mass, so the mass will decrease. What will happen to the mass of the copper electrode? Definitely it will increase, because there is copper 2 plus gaining electrons forming copper. And then write down the net cell reaction. I've shown you that to write the net cell reaction, you need to know the half reactions. The zinc stronger reducing agent, we said we reverse the stronger reducing agent reaction. The stronger oxidizing agent gains electrons to form copper like that. And for overall cell reaction, we said that you first cancel the equal electrons, so the electrons must be balanced. What is on the left, you write on the left. What is on the right, you write on the right. So you're able to write that and get that. Will the electrons move from zinc to copper? Already you know that zinc is the anode, so electrons always move from the anode to the cathode. Definitely they will move from zinc to copper half cell. Use scientific cell notation. You see the cell notation, remember we talked about it. We said A, I can write it here, A, B, C. On the anode, we have zinc forming zinc 2 plus, and then on the plus 2 electrons, that is the half reaction. But now on the cell notation, A is zinc forming zinc 2 plus. I said you make a solid line because zinc is solid, zinc 2 plus is aqueous. That line, it means phase boundary. And then they are separated by the salt bridge, and then you have copper 2 plus forming copper. So you're taking them from here. Zinc is forming zinc 2 plus, copper 2 plus is forming copper, and then you are able to do that. I said it will even be happier if you indicate the concentration of the zinc 2 plus to say is 1 mole per cubic decimeter, and the concentration of copper 2 plus is 1 mole per cubic decimeter. And remember, this question comes with 3 marks, so you are able to get your 3 marks. I hope you have seen, and you will continue to practice as many questions as possible, and then as we go on. So I just wanted to summarize and say this is what we looked at. We looked at the oxidation half reaction, reduction half reaction. We looked at the issue of the anode, the cathode, the reducing agent, oxidizing agent, the electrolyte. I hope these ones you are singing about them, you are able to know. I've explained nicely to you to say, okay, they were supposed to calculate the EMF of the cell. And at equilibrium, we said the EMF equals to 0. And then we are saying now as well, you must be able to know the standard electrode potential, which is what we used on the table 4b. We said standard stands for the standard conditions, which is initial concentration of 1 mole per cubic decimeter, temperature of 298 kelvins or 25 degrees Celsius, and pressure of 101.3 kilopascals. Remember, with pressure, we're saying this one affects only gases. And then that's what we have done. I hope you have enjoyed the lesson. You will continue to do many activities just in time. On the 15th of August, 2025, at 2:30 to 4 o'clock, we'll be doing electrolysis, which is now question 9, the last question in terms of paper 2. We'll be doing that one. And then, as always, I would like to say thank you, closing with those words of Albert Einstein that says, anyone who has never made a mistake has never tried anything new. Thank you very much.